Howdy, and welcome to Science News. A quick read through that, and just let's go. Astronomers spotted shock waves shaking the web of the universe for the first time. The observation could offer an indirect look at large-scale magnetic fields in the universe. In this simulation of the cosmic web, shock waves along filaments and around clusters emit radio light pink as they ripple through magnetic fields. Cyan. Cyan. 6 hours ago. For the first time, astronomers have caught a glimpse of shock waves rippling along strands of the cosmic web, the enormous tangle of galaxies, gas and dark matter that fills the observable universe. I thought dark matter is not observable, but anyway. Combining hundreds of thousands of radio telescope images revealed a faint glow cast as shock waves sent charged particles flying through the magnetic fields that run along the cosmic web. Spotting these shock waves could give astronomers a better look at these large-scale magnetic fields, whose properties and origins are largely mysterious. Researchers report on the February 17th Science Advances. Finally, astronomers can confirm what so far has only been predicted by simulations, that these shock waves exist, says astrophysicist Markus Brücken of the University of Hamburg in Germany, who was not involved in the study. At its grandest scale, our universe looks something like Swiss cheese. Galaxies aren't distributed evenly through space, but rather are clumped together in enormous clusters connected by ropey filaments of dilute gas, galaxies, and dark matter, and separated by not quite empty voids. Tugged by gravity. Galaxy clusters merge, filaments collide, and gas from the voids falls into filaments and clusters. Yeah, you know. You need probably an up and down in order to say that something is falling somewhere. So it's a matter of perception. But anyway, in simulations of the cosmic web, all the action consistently sets off enormous shock waves in and along filaments. Filaments make up most of the cosmic web, but are much harder to spot than galaxies. While scientists have observed shock waves around galaxy clusters before, shocks in filaments have never been really seen, says astronomer Reinoud van Weeren of Leiden University in the Netherlands, who was not involved in the study. But they should be basically all around the cosmic web. Shock waves around filaments would accelerate charged particles through the magnetic fields that suffuse the cosmic web. When that happens, the particles emit light at wavelengths that radio telescopes can detect, though the signals are very weak. A single shock wave in a filament would look like nothing, it'd look like noise, says radio astronomer Tessa Wernstrom of the International Centre for Radio Astronomy Research in Crawley, Australia. Instead of looking for individual shock waves, Wernstrom and her colleagues combined radio images of more than 600,000 pairs of galaxy clusters close enough to be connected by filaments to create a single stacked image. This amplified weak signals and revealed that, on average, there is a faint radio glow from the filaments between clusters. When you can dig below the noise and still actually get a result, to me, that's personally exciting, Wernstrom says. The faint signal is highly polarized, meaning that the radio waves are mostly aligned with one another. Highly polarized light is unusual in the cosmos, but it is expected from radio light cast by shock waves, Van Weeren says. So that's really, I think, very good evidence for the fact that the shocks are likely indeed present. The discovery goes beyond confirming the predictions of cosmic web simulations. The polarized radio emissions also offer a rare peek in at the magnetic fields that permeate the cosmic web, if only indirectly. These shocks, Brücken says, are really able to show that there are large-scale magnetic fields that form something like a sheath around these filaments. He, Van Weeren and Wernstrom all note that it's still an open question how cosmic magnetic fields arose in the first place. The role these fields play in shaping the cosmic web is equally mysterious. It's one of the four fundamental forces of nature, right? Magnetism. Wernstrom says. But at least on these large scales, we don't really know how important it is. So, magnetism. One of the four fundamental forces of nature, right? Magnetism. So this is just a random page I picked up where they are talking about magnetism as well. EIA, Gov, some government. Okay. Basics. The spinning of the electrons around the nucleus of an atom creates a tiny magnetic field. The electrons in most objects spin in random directions and their magnetic forces cancel each other out. Magnets are different because the molecules in magnets are arranged so that their electrons spin in the same direction. This arrangement and movement creates a magnetic force that flows out from a north-seeking pole and from a south-seeking pole. This magnetic force creates a magnetic field around the magnet. Have you ever held two magnets close together? They don't act like most objects. If you try to push the two toward the two north poles or two south poles together, they repel each other. But if you put a north pole and a south pole together, the magnets will stick together because the north and south pole attracts each other. Just like protons and electrons, opposites attract in magnets. Magnetic fields can be used to make electricity. If you have noticed in the article I read before, they were talking about magnetism. But not one single word about electricity. Nothing. The properties of magnets are used to make electricity. Moving magnetic fields pull and push electrons. Metals such as copper and aluminium have electrons that are loosely held. Moving a magnet around a coil of wire or moving a coil of wire around a magnet pushes the electrons in the wire and creates an electrical current. Electricity generators essentially convert kinetic energy, the energy of motion, into electrical energy. And since I'm not a scientist, I would like to give a scientist the word. Donald E. Scott, cosmic power lines. The Birkeland currents, which are the connections between planetary bodies, the connections between galaxies, and so on.
Here's another, this is of course just an artist's impression, but I think that is probably more like, at least the theoretical, the archetype model. The important thing there is that you'll notice that the white lines are the, I hate to use the word field lines because it's a touchy subject with me, but it shows the fact that the magnetic field wraps both ways. Okay? This next one is, this is very much like one that Tom had on. And with one minor exception, it's all wrong, in my opinion. We have the accretion disk, we've got black hole, we've got the event horizon, and it's all nonsense. This is the astronomer's explanation for what you just saw at M29 or the other drawings that I just showed you. The one thing they have right is the magnetic field lines. You see the spirals coming down. So a cross-section of the Birkeland current at the location of the pinch contains the spiral paths of the magnetic field. That's true. That's correct. There is a spiraling, sort of looks spiraling anyway. We'll talk about that in a minute. So if we look down at the cross-section, the cross-sectional disk, which is really, the disk that's defined by that ring of the energetic neutral atoms, the Ibex ring that we just got through looking at. We should see a spiraling magnetic field. The little blowout diagram with the event horizon, the black hole, and the accretion disk is a total F. Flail. It fails. Don't believe it. Anyway, here's some diagrams that the team that ran the Ulysses space program, that went up as high over the poles of the sun as anything has ever gone, to take a look at what's going on at the sun's poles. We never really have gotten above the poles. But as close as we've gotten, you can see here that what is coming out of the bottom of the sun is this ever-widening spiral of a magnetic field. And if you look at the North Pole, which Ulysses also did, you see the same thing. I think the diagram here is a little bit more accurate and a nicer diagram. But essentially has the same material in it. Notice that the green disk on the solar equator, here they don't show any spirals, any spiraling in, but they do show that ring, which is the E and A ring, and they do show the magnetic field lines that are circling around. And this, I submit to you, is very characteristic of the Birkeland current. In fact, it looks exactly like that, and you all probably recognize that, or maybe many of you, I'm sure, do. That's Eugene Parker's description of the solar magnetic field. Remember the words, the magnetic field of the sun swirls like a ballerina's skirt and has ripples and disappears into infinity. Well, it doesn't disappear into infinity. That's one of the things that got me into this, was when I heard astronomers talking about magnetic fields that went to infinity. Magnetic fields are closed paths, and they can't go to infinity. So, sorry, Gene, that's not right. But the idea of a spiraling like this as we get close to the equatorial plane of the sun is quite correct. What he's also shown in there, if you look very closely, I don't know if you folks can see it, but you notice inside here that you can see the orbits of the inner planets. And this is probably Jupiter or Saturn around out here.
Yes, I recommend you to watch this, and probably also part 1, if you haven't yet. But I leave it here. They are getting closer, but still avoid the word electricity. Funny. Thanks. Bye.